Hey everyone, welcome to lecture 5.1 on vectors. In this lecture and in the next few videos for chapter 5, we're going to talk about three-dimensional space and higher dimensional space in a little more detail so that we can do multivariable calculus towards the end of the course with a little bit more rigor. So the goals in this first lecture on vectors will be to discuss the difference between vectors and numbers, which we'll call scalars, and points, which will be points in three-dimensional or higher dimensional space. We'll also learn how to add and subtract vectors and to multiply by scalars, those real numbers. And we'll finally express real-world vectors in terms of their components. Real world meaning coming from some problem where we have to interpret the information in the problem in terms of vectors, and the components of their vectors will have some sort of meaning. And I should also mention, I said three-dimensional and higher, but vectors also live in two dimensions, the xy plane, and we'll stick with that as our foundational example for the first few slides. We'll also use three-dimensional space to understand higher dimensions as well. So to get started, in two dimensions right away, we can define what a vector is. A vector is going to be the data or the information of a magnitude, which is also thought of as the length of the vector, and a direction in two-dimensional space. Now that's a sort of abstract definition. A vector has two pieces of information, the length, and the magnitude, and the direction. But typically it's easier to visualize and to understand vectors using the notion of an arrow. So you should think of a vector as an arrow that we've drawn in the xy plane in two-dimensional space. And every arrow has a magnitude, which is just the length of that line segment representing the arrow, and a direction that it points. And I'll make a comment on why that's all the information that a vector contains in a moment. Where it lives in the xy plane actually doesn't matter, but we'll get there in a moment. Really, the constant of that is the next sentence in the definition that says two vectors with the same magnitude and the same direction are considered equal. They're the same vectors. So here are four different vectors in the xy plane that we've represented using arrows. You can see u and w share a common base point or a common starting point, and then the arrowheads indicate where their ending points are as we travel away from the starting point. The vectors v and m have different starting and ending points. They all seem to have different lengths. If we were to measure carefully, u, v, and w, the first three vectors you see on the left, all have the same magnitudes. They have one of their pieces of information the same, the length. They don't have the same direction, all three of them, but u and v, you can see, actually have the same direction. So u and v are two different arrows that we've drawn in the xy plane. They have the same magnitude or length, if you were to carefully measure with a tape measure or ruler, and they also have the same direction. They're pointing in the same direction. So by definition, we call these the same vector, even though we've drawn them in two separate locations. Those are the only two vectors in this picture that are the same. W has a different direction than all of the other vectors, and M has a different length or magnitude than all of the other vectors. So U and V are equal, W and M are two separate vectors. So we really have a picture here with four different arrows, but only three different vectors drawn. This is something that when you first see it, it takes a little bit getting used to, that different arrows actually correspond to the same vector. But as we start to interpret this in terms of displacement, what the components of vectors really mean, this will become a little more clear, I think. So here's some examples out in the real world of vectors and some things that are not actually vectors. So if we consider the face of the Earth to be the xy plane, okay, I'm not a flat earther, I swear. Let's just pretend that in a certain area, we can lay a map flat and represent things as some portion of the xy plane, and ignore the fact that there's a curvature around the sphere that is the Earth. We can represent things using vectors, such as traveling 3 miles south from point A to point B. We can draw an arrow. The length of the arrow will be 3 miles, and the direction will be straight south. And that the data of 3 miles, the length, and south, the direction, gives you an arrow or a vector. More abstractly, more in the physics realm, the force that a magnetic field applies to a charged particle is in fact a vector. It has the strength of the force, that's the magnitude, and the direction of the force that it's applying on the charged particle, thereby inducing some sort of motion in the particle that is the direction. So that's a vector, a force vector. The velocity of an airplane, or in general velocity of any object as it travels through space, is going to be represented by a vector. The magnitude of velocity, in fact, is speed, just as a pure number, miles per hour or kilometers per hour or meters per second. That magnitude of the vector is the speed, and the direction of velocity is the thing that distinguishes it from speed. It actually has a direction, and therefore is represented by a velocity. I'm calling these vectors in 2 dimensions, but really the velocity of an airplane as it rises and falls in the air is a 3-dimensional vector, and things like force can be represented in higher dimensions than just 3 dimensions. Here's some non-vectors that don't contain a magnitude and a direction component. The number 17 only has a number attached to it. You could call that the length or magnitude of something, but it doesn't have a direction. Likewise, the mass of an automobile, which in contrast to its weight, which is really a force vector, the mass of an automobile is just a single number. It tells you how much mass, how much material is in that automobile. If you know a little bit about the difference between mass and weight from a science class you took in high school, weight, which would be in pounds rather than in grams or kilograms, actually is a vector. It's the force, it's a representation of the force of gravity acting on that object. And since gravity is uniform for most small enough things on the surface of the Earth, then we think of weight as a single number. But it's really the length or the magnitude of the gravity vector acting on, or the gravity force acting as a vector on your car or your body or whatever it is. Here are 2 more non-vectors. 3:15 p.m. is just some coordinate in time. It doesn't have any direction. And finally, Atlanta, Georgia doesn't really have any sort of numerical information. But even as a point on the map, if we represent things geometrically, it doesn't have a length or a direction. And these are some of the key differences that we use to distinguish between vectors and scalars, or real numbers, and points in a moment. So just to give things a little more notation, a vector, which we'll write as just the letter V, or V with an arrow over the top, in general, in the XY plane and in higher dimensions, can be represented as an arrow from point A to point B. And if we specify the starting and ending point, or in fancy terms, the initial point and the terminal point, A and B, then we can represent that vector with the notation AB with an arrow on top. And here's an immediate result or fact, which we'll call a theorem, that is pretty useful for understanding vectors geometrically. So in the XY plane, if I specify 4 points, A, B, C, and D, and I can even give them coordinates, which we'll use in a moment to study this type of problem. If I have 4 points, A, B, C, and D, and I look at the vectors A, B, and C, D, then these are the same vector, meaning they have the same direction and the same magnitudes or lengths. This is true if and only if the 4 points form a parallelogram. And in parentheses, it says perhaps a squished parallelogram. I actually want you to think about what that would mean rigorously. What does it mean to have a parallelogram that's squished? And what would that mean in terms of the vectors being equal? So the geometric notion of a vector is really intuitive. You draw an arrow, you just take an arrow and throw it at the XY plane, or throw it at the wall at home, and see where it points and how long that arrow stretches out to be. That gives the 2 pieces of information of a vector. More useful, I think, for doing actual calculations mathematically is the notion of coordinate notation for a vector. So if we are considering vectors in the XY plane, we can represent any vector, which again is uniquely specified by its length and its direction, instead by a pair of coordinates. We'll call them the X and Y coordinate, but you should really think of the X and Y coordinates of a vector not as giving some point in the XY plane, but as telling you the displacement along the arrow representing that vector. So for example, if we have a vector V that's represented by, or that's given by a starting point A, which is 2, 3, and an ending point B, which is 5, 1, then the vector AB can be represented by the coordinates 3, -2. And the way to think about this is that the x coordinate 3 is the displacement in the x coordinates of the points. Traveling from A to B, we go from x equals 2 to x equals 5, and that's an increase of 3. So AB, the vector, has x coordinate 3. On the y coordinates, traveling from A to B goes from 3 down to 1. So that's a decrease of 2, and the y coordinate of the vector is -2. You can see this drawn in the picture again. You can see that the arrow from A to B has displacement coordinates over 3 units in the x direction, down 2 units in the y direction. And this, in fact, fits into a triangle with legs of lengths 2 and 3. And now you can start to see ways of recovering the length or magnitude of the vector and also the direction using trigonometry. So here's a theorem that's similar to the parallelogram theorem we had before, except it's a little easier to state and it's much, much easier to check than the parallelogram theorem. We have two vectors v and u, and we only know their coordinate representations, such as 3, -2 on the previous slide, then they are the same vector, meaning they have the same length and the same direction, if and only if their two coordinate representations match in every component. So this is more powerful than the parallel. I mean, it's the same, really the same statement as the parallelogram theorem, but it's more powerful for us because it's easy to check. If you write down two vectors and they have the same coordinates, then they are the same vector. One thing that we can do, well, one thing that I haven't said yet that we can do is from the coordinate representation, we can compute the length of the vector. And that's essentially by doing the Pythagorean theorem on this triangle. We'll practice with this in a moment. But another thing that we can do is we can compute slope. And by knowing slope, we can understand the direction of a vector. So if I have a vector a comma b, a is the displacement in the x direction, b is the displacement in the y direction, then we can form the slope of the vector by computing rise over run, or b over a. You should think of a vector as a line segment, and it has a particular direction. The arrowhead tells you which way to travel. But because it's a line segment, it's part of a larger line, and the slope of that line is this b over a number. So let's get into some more examples here. Every point in the xy plane is distinct from a vector. It's just a point. It has no notion of length or distance. However, if we remember that there's always the distinguished point in the xy plane, namely the origin 0, 0, then specifying any point in the xy plane also gives us a nice notion of vector, which is the displacement from the origin out to that point. So I want to remind you that there's a difference between vectors and points. Points don't have any notion of length or direction, but if we remember the origin and remember that we traveled from the origin out to this point, that is exactly a vector in the xy plane. The nice thing about this is the coordinates are exactly the same as the unique coordinates of the point. For example, the x coordinate -5, y coordinate +1 point, shown here as a black dot, has the same coordinates as the vector from the origin out to that point, -5, 1. Notice that there are many different vectors that are equal to -5, 1. Namely, if I pick any black dot anywhere in the plane and move 5 units to the left and 1 unit up, that vector, in this case maybe a to b, will have the exact same coordinates as the vector from 0 out to this point. And it's useful because if we can compute things starting at the origin out to any point and compare that to any other situation out here and just make our computations on vectors of this form, then, well, the purple arrows are really the same vector. So our computations are made easier by using vectors of this form. We can do a bit of arithmetic, meaning we can combine vectors in different ways. And the easiest way to do this is if I have two different vectors, v and u, and I want to add them together, well, I can add them coordinate-wise, or I can add them geometrically. I'm going to show you the two different ways of thinking about this. It gives the same result, by the way. So the sum of two vectors is done by laying them end to end and adding up the results. Or in other words, if I take v and I want to add u to it, I'm going to take v, represent it as point A to point B vector, and then take the vector u and start it at the ending point of v, and let its ending point be wherever the vector u takes us. Remember, u has a length and a direction, and we travel along that arrow. Wherever we end up, we'll go back to the start of v and travel along both arrows together and call that v plus u. I want you to think about how this works with coordinate notation. I'm going to take a drink of water and I'll be right back. So geometrically, I think this is pretty satisfying. We can just lay the arrows end to end, add them up, and we get a new vector called v plus u. Things are even better in coordinate notation, where we have numbers and we like to add numbers together. You'll see that the vector v is represented in coordinates by 1, 3. Check that that is the right description for v, and likewise that the vector u that you see is represented in coordinates by 3, -1. If I add these coordinates together, I get the vector 4, 2 in coordinates. And I want you to check visually by looking at this plot over here that 4, 2 is exactly the coordinate description of this vector v plus w in the picture. So if we want to compute the sum of two vectors, we can do it both geometrically with a picture and algebraically or arithmetically using the coordinate notation. There's another operation on vectors which will be important for us, which is the notion of scalar multiplication. So for historical reasons, we will call numbers, real numbers, scalars. And really the reason is that we're going to multiply vectors by real numbers, and the result of that operation will be stretching or scaling the vector by that number. So that's really where the word scalar comes from. So to be more specific about this, if we have a scalar, a real number lambda, and a vector v, we can produce a new vector called lambda times v, which is the vector with the same direction as v, but lambda times as long, or lambda is going to change only the length of the vector, not the direction. Geometrically, what this looks like, let me go back a slide. Geometrically, if I start with this purple vector v, and I multiply by the scalar 2.14, that's real number, then 2.14 times v is the blue arrow with the same direction as the original v, but 2.14 times the length of v. We will say that whatever real number lambda we multiply by, that result lambda times v is called parallel to v. And notice that I could choose lambda to be any real number. In particular, I could choose lambda to be 0, in which case the 0 vector, which has starting and ending point at the same point, or has coordinates 0, 0, is parallel to every other vector because I can multiply any vector by 0 to get the 0 vector. Likewise, I could, or for a different type of parallel vector, I could multiply by a negative number, like -1, and that's going to swing our vector in the opposite direction. So parallel, in other words, means the vector is 0, or pointing in the same direction as our starting vector, or pointing in the opposite direction as our vector. We'll learn more about parallel vectors later in this video. In coordinates, scalar multiplication is really easy to compute. If we have a number like 2.14 in the picture or 2.5 in this example, we want to multiply by a coordinate vector 6, 4. We just distribute this number into each of the two coordinates. 2.5 times 6 is 15. 2.5 times 4 is 10. And you get the outputs, the coordinates of the output vector, which is 2.5 times the input vector. So I want to take a moment and think about how to do different calculations like this on the pictures and on the components of vectors u and v. So this won't have specific vectors u and v involved, but you can imagine choosing two arrows in the xy plane or giving them coordinates for this next part. We'll do this together, but if you want to try to sketch this out on your own first, I encourage you to pause the video and do so now. So let's suppose we have two vectors u and v in the xy plane, and the vectors could be starting at any start points and end points, but I'm just going to assume that both of them are starting at the origin. Remember that we can always translate these vectors around and stick their starting points anywhere we want, but their endpoints will be different in general. So we have two vectors u and v. How would we calculate the sum 1/2 u plus v? Well, let's start with the 1/2 u part. 1/2 u says take the vector in the same direction as u, but 1/2 the length. So that's going to look like this. Actually, I'm going to move that label to the other side for a moment. So that's the first step. And next, if I want to compute the sum of this vector and the v vector, all I have to do is take the v vector and start it at the place that 1/2 u ends. It looks like that's about the same. This is also v. Maybe let's make that red just to match with the style here. And in order to get the sum of these two vectors, the purple one, 1/2 u, and the red one, v, I'm just going to do end-to-end addition and draw a new arrow that starts at the origin, the starting place of the purple arrow, and ends at the same place as the red arrow. So that's 1/2 u plus v. So that's how we do things geometrically. What would happen if instead we had components of u and v given by a, b, and c, d? So let's think about how to do this algebraically now. So first of all, let's write in those components a, b for u, and c, d for v, and think about how to first scale by 1/2 and then add the resulting vectors. Well, scaling means we're just going to scale each individual component. I'm going to scale the x component by 1/2 and the y component by 1/2. Sorry, I didn't mean to. I said y out loud, and I meant to write b. And we'll deal with the CD part in the next step. Now I have two vectors, and I want to add them together. And the algebraic way to do that, or the coordinate-wise way to do that, is to add the coordinates individually. So I'll have 1/2 a plus c and 1/2 b plus d. And in the future, we're probably going to skip straight from this step down to this step and not think too much about it, but it's important to see how these two different procedures happen independently. So we first scale and then we add. And actually at this point, I want you to think about what would happen if we added first and scaled. We added u and v first and then scaled by 1/2. Would you get the same vector or would you get a different vector? And you can think about this now geometrically in terms of the picture. First add the blue vector and the red vector and then scale by 1/2. And you can also think about it algebraically in terms of the coordinates and see what the answer is. So let's return to the lecture slides. I want to introduce one more type of notation that you might see. I won't use this too much in class, but it's a good one to know about, especially if you're going to study any sort of physics. And the following are two types of important vectors called the standard basis vectors in R2. R2, again, is our notation for the XY plane. I'll usually say XY plane out loud, but that's what R2 means. The standard basis vectors, that's a typo. It's a LaTeX command that showed up. So forget about that. The standard basis vectors in the XY plane are the vectors 1, 0, and 0, 1. For physics reasons, we call these I and J. And it doesn't matter so much what these mean. This is not the imaginary number I. But I and J are just, in geometric terms, are the vectors 1 unit in the x direction and 1 unit in the y direction, or they stick along the two axes, the x-axis for I and the y-axis for J, and they each have length 1. The reason that they are called the standard basis, if you've seen any linear algebra before, is that every vector in the xy plane can be uniquely specified as what's called a linear combination of I and J, which in simple terms just means I can take some number of copies of I and add it to some number of copies of J, where number of copies could be a positive or negative number. For example, the vector 3, -5, 3 units of x displacement, -5 units of y displacement, can be written as 3 i's minus 5 j's. That's what's called a linear combination of I and J. And you can check for yourself that this is the right combination. You can also do this geometrically by taking, stretching the x directional I by 3, stretching the y directional j by -5, which means flip it over and stretch by 5, and then add those together head to tail to get the vector 3, -5. Now that we have a notion of coordinate notation and also the standard basis notation, ij, we can compute length or magnitude algebraically. This is what I was alluding to before with the triangles, but here's the official definition of the magnitude of a vector. If our vector is given by a, b, which can also be written ai plus bj, then the length or magnitude of the vector, denoted with the absolute value bars of v, is equal to the square root of a squared plus b squared. I want you to pause the video now and draw a triangle that demonstrates that this is the correct formula using the Pythagorean theorem. If v is written as ai plus bj, you'll see that this vector here, a copies of I, and this vector here, b copies of j, have magnitudes that correspond to two legs of the triangle. So this is the length of a vector. And let's practice by computing the length of the vector on the previous slide, 3, -5. So by definition, the magnitude is we first want to write the vector as, well, we write it as a coordinate vector, 3, -5. The definition on the previous slide said we should think of it as AI plus BJ. Here it's 3i and 5, sorry, it's -5j. But we're going to skip that step in the future because it's redundant. What we're just going to do is take the x component squared, the y component squared, and then we'll take the square root at the end. This is the formula for computing length. And in this case, we have 9 and 25 under the radical. And let's see, 9 plus 25 gives me 34. And I don't know the square root of 34 off the top of my head, so I'll leave it as a square root. So that's the length of this vector. If I drew this in the xy plane, by the way, I go over 3 and down 5. Here's the arrow 3, -5. Write it. So the point is 3, -5, and the arrow is bracket 3, -5. Would you have guessed that the length here is square root of 34? And if you didn't know what the length was and you didn't remember this formula, how would you come up with that length on your own? There's one more notion of length that I want to talk about. And actually, I mentioned earlier, we'll discuss direction a little more in this video. It's not until the next video that we'll have a more rigorous definition of direction. So far, we just have slope in this video. But to wrap up our discussion of length or magnitude, we'll call a vector a unit vector if its length is 1. So it has exactly 1 unit of length, whatever direction it's pointing. For any vector v, we can form a unit vector pointing in the same direction as v, which means it's parallel to v, by scaling v down by its length. So that's what this notation means. If we take v and we divide out by the length, that's some scalar multiple, the reciprocal of the length of v, times v, that gives us a new vector. And this is a unit vector. You can check by the definition of length that this has length 1, and it has the same direction as v. So one small comment on angles before we do the full discussion in the future is, sorry, I'm just skipping around for a sec. Yeah, we're going to talk about angles in full in the next video, but I just wanted to double check it's not coming up. So one small comment about angles, which is going to be our notion of keeping track of direction of vectors, is it's easy to tell when two vectors form certain types of angles. We've already seen that parallel vectors are ones that are pointing in the same direction or the opposite direction. And if you think about the possible angles between vectors that allow them to be parallel, there are really only 2 options. It's an angle of 0 degrees or radians and an angle of pi radians or 180 degrees. That's what it means to be parallel. The midway point, which is if they form a 90-degree angle, is what's called perpendicular or orthogonal. And these are the types of angles that we'll handle in this video. We'll talk about arbitrary angles in the next video. So 2 vectors don't necessarily, if we have 2 vectors in the plane that are just between any 4 different points, they may not share a base point. They may not intersect to form an angle. However, if we line them up so that their initial points or their starting points are the same, we can measure an angle between them. And given that 2 vectors are only specified by their length and their direction, all that we need to do is line everything up so that their base points or their initial points are always at the origin, and we can start making angle measurements there. So if we have 2 vectors and they form a right angle or an angle, or they have an angle of pi over 2 radians, we'll call them orthogonal, and that's synonymous to perpendicular. If instead they make an angle of 0 or pi radians, then they'll be called parallel. And notice that this is the same definition of parallel as we had earlier in the video. How do we do things in higher dimensions? Well, everything is a lot harder with the geometry. It's hard to draw in 3 dimensions and higher. However, the coordinate notation is really helpful in this case. If we want to make sense of a vector in n dimensions, the definition is the same. We just need to have a notion of length and a notion of direction. And we know how to write down points in higher dimensional space. We just specify n different coordinates, the x1 through xnth component. And to form a vector, we can just take the displacement of each of those components. For example, in 3 dimensions, the vector stretching from a equals 2, 4, 1 to b equals 5, negative 1, 3 has displacement coordinates. Well, 5 minus 2 is 3, negative 1 minus 4 is negative 5, and 3 minus 1 is 2. So this vector 3, negative 5, 2 is a 3-dimensional vector. In order to represent things using the standard basis, we actually need a third element pointing in the z direction by 1 unit, and that's usually denoted k. You see the pattern I, j, k. After that, we kind of run, there are more letters to use, of course, but physicists use different notation for higher dimensional spaces. But I, j, and k, we can write anything, any vector like 3, negative 5, 2 in the form 3i minus 5j plus 2k. And higher dimensional things, again, have different notation. Things the notation varies. Typically, you'll see something like E1 through EN. E stands for elementary, if you're curious about these things. But we can represent things in coordinate notation to be concise. The length of the vector is something you may not have seen before in higher dimensions, but it's just really a generalization of the same distance formula that we have in 2-dimensional space. If we take each of the components of our vector, each of those displacement values, square it, add all of those displacement squared up, and then take the square root at the end, then we get the length of the vector. Now, I encourage you to draw the 3-dimensional version of this, which would be a1 squared plus a2 squared plus a3 squared, and take the square root using the Pythagorean theorem and triangles, just as I encouraged you to do earlier for the 2-dimensional length formula. Finally, angles between vectors in higher dimensions, which we'll talk more about in detail in the next lecture, are a little harder to deal with, but it's not so much harder that we can't do anything with it. So if we have any pair of vectors in 3 dimensions or higher, we're first of all going to line them up so that they have the same initial point. And we can even make that the origin, just like we did in 2 dimensions. And next, because we only have 2 arrows that are potentially sticking in 2 different directions, then they're going to lie in a plane. And now that they're lying in a plane, we can pretend that it's just the XY plane, even if it's a different plane. And in whatever plane that is, the angle between them will be some well-defined angle in the XY plane. So it's a 2-dimensional measurement, meaning we can form a plane and then compute the angle by drawing it as the XY plane. There's actually no way to measure clockwise or counterclockwise in higher dimensions. So it doesn't make sense to say that the angle is positive or negative. It only makes sense to specify that the angle is between 0 and pi, or between 0 degrees and 180 degrees. And if we specified which one was the left or the right arrow, like we can do in 2 dimensions, then we could have a notion of positive or negative angles. But in general, we'll just say that these 2 vectors form an angle of something between 0 and pi radians. Here's a picture denoting 2 vectors in 3-dimensional space where we've lined up their initial points to be the same. They lie in some plane, and the angle drawn in gold there between them is some notion that we can make sense of. And we'll start doing that in the next video. So here are some summary questions from this video. How is a vector similar to a point and to a number? And in contrast, how is a vector different from a point and different from a number? If I hand you 2 vectors, how can you tell if they point in the same direction or in opposite directions? And finally, if u and v are position vectors corresponding to 2 points P and Q, how are the vectors u and v related to the displacement vector P, Q? And I encourage you for each of these 4 questions to think about it in 2 ways, both geometrically with a picture and algebraically in terms of coordinates. That's it for this video. I'll see you next time.